This is question number 2, part 1. This is about Newton's third law. There we go. Okay, so in his Principia Mathematica, Newton expressed his third law of motion as to every action there is always opposed and equal reaction. State what Newton meant by this law. All right, and you wouldn't need to write all this in your answer. I wanted to bring up with this the horse and cart problem. Okay, so what this problem is there is a horse pulling on a cart, right? So the horse is exerting a force on the cart, but if for every action there's an equal and opposite reaction, the cart should exert an equal and opposite force on the horse, and the cart won't go anywhere, the horse won't go anywhere. Well, obviously that's not true. So why is this the case? Okay, so first of all, let's take a look at the F push here, F equals push. So the way that we walk and the way that this llama is moving is that the llama is pushing off the ground, okay? And the force that the llama exerts on the earth, okay, is equal to the force that the earth exerts on the llama, all right? But the reason that we notice the llama accelerating and not the earth is that the earth has a very, very large mass, and it'll have a tiny, tiny, tiny acceleration. The llama has a very tiny mass compared to the earth. This is not to scale at all right? And the acceleration is very large compared to that of the earth. But with this teeter-totter here, you can see F equals ma, all right? And force of the earth on the llama is equal to the force of the llama on the earth, all right? Now, the llama pulls on the cart, okay? And the cart pulls on the llama, all right? With an equal and opposite force. So if there were no friction, okay, the reason that the cart is pulled is because you're talking about two different systems of forces here. Newton stated that for every action there's always an opposed and equal reaction to the force, but he's talking about pairs of forces. So he's talking about the force of the earth versus the force of the earth on the llama versus the force of the llama on the earth, all right? Or the force of the llama on the cart versus the cart on the llama. But in this case, the llama is pushing off the earth and creating this larger force than the cart pulls with, all right? So even if there were no friction, the cart would move. In the friction case, we're looking at the wheel here, okay? And I'm not going to get into rolling friction. It's very complicated. You can look it up on Wikipedia if you want. But I drew this simple diagram here, and it's not really that accurate, but it kind of gets the point across. The wheel's spinning, and it's moving backwards, and the ground is pushing in a forward. The friction on the ground is pushing in a forward direction, resisting its motion. It doesn't actually work like that, and if you want to know more about it, come and ask me. It kind of works like this, but kind of not. There's more to it than that. But I just wanted to show that because it's the wheel ground system, okay? And we can also call this the wagon ground system. The wagon's trying to go forward, the ground is pulling it backward. This is a more simplified version of it. I just put this in here. Hopefully it doesn't confuse you. Look at this one here, okay? If there's friction involved, we're only looking at the cart versus the friction on the ground. The cart is being pulled forward. The friction is pulling in the opposite direction backwards, or pushing in the opposite direction backwards. And the pull is greater than the friction. So with this problem here, you're looking at different systems of forces, different pairs of forces, and that's why for every action, for every force, there has to be a force opposing that. Okay, and you can still have the horse and cart moving along. All right, let's move on to B here. A book is released from rest and falls toward the surface of the Earth. Discuss how the conservation of momentum applies to the Earth-book system. Okay, first of all, I'm going to look at the momentum at the collision after they're both moving towards each other. Okay. Actually, I should talk about this one first. Okay, I'll get to that one. The book falls toward the Earth, but the Earth actually is pulled toward the book slightly because the force of gravity on the book is equal and opposite to the force of gravity on the Earth. All right. So the Earth actually is pulled toward the book slightly, and the book is pulled toward the Earth with the same force. But if you use this teeter-totter up here, the Earth has a much larger mass and very little acceleration. The book has a much smaller mass, very large acceleration. Okay? Momentum is mass times velocity. At the moment of collision, the Earth has a very, very large mass and a tiny, tiny, tiny little velocity. But it does have some velocity, but it's too small to really count. So we're not really going to worry about it. The book has a tiny, tiny mass compared to the Earth and a large velocity. But the momentum of the Earth and the momentum of the book are equal and opposite. Okay? Because the book is falling towards the Earth is falling towards the book. And because their momentums are equal and these are vector quantities, you add them together and you get 0. Okay? Over here, I showed that the change in momentum of the book during the fall is equal to the change in momentum of the Earth during the fall. So the impulse of the book and the impulse of the Earth are equal and opposite. All right, if you have any more questions about this, you can come and see me. Oh, let me just read off what they're looking for with the answer. So they said forces on the Earth and book are equal and opposite. Changes in momentum of the Earth and the book are equal and opposite. The change in momentum of the Earth book system remains constant. All right, so it's 0. All right, so I will see you in the next video, which is the second part of this question. Okay, see you in a minute.